Two GE CF34 tinny turbofan engines designed for subsonic commercial airline service are installed on the EMBRAER E190. Each engine is housed in an aerodynamic nacelle and suspended from a pylon attached to the lower wing surface. With a fan bypass pressure ratio of 5.4 to 1, a booster pressure ratio of 2.3 to 1, and a compressor pressure ratio of 11.4 to 1, the engine produces a maximum power of 18,820 pounds at ISA condition. The engine has a total length of 4.53 meters, 178.2 inches, a diameter of 1.85 meters, 72.8 inches, and an engine dry weight of 1,667 kilograms, 3,675 pounds. The cowls which enclose the engine form the engine nacelle. The nacelle provides protection for the engine and accessories and also ensures smooth airflow around the engine during flight. The following cowls make up the engine nacelle: 1 inlet cowl, 2 hinged fan cowls, 2 hinged thrust reverser cowls, 2 hinged core cowls, and the primary exhaust nozzle. The inlet cowl is a fixed interchangeable aerodynamic fairing which supplies the inlet airflow to the fan and to the core section of the engine. The inlet cowl is mounted on the forward face of the engine fan case and consists of an inlet lip, a forward bulkhead, an outer barrel, an acoustic inner barrel, an aft bulkhead, and an aft flange. The inlet lip is formed in a single piece and forms with the forward bulkhead a D-duct which contains the swirl nozzle. The purpose of the swirl nozzle is to deliver engine anti-ice air to the interior of the D-duct to heat the inner surface to prevent ice accumulation on the exterior surface of the lip skin. The anti-ice air is exhausted through 6 anti-ice exhaust ports located at the 6 o'clock position. The outer barrel structure is made of an aluminum alloy and has panels to give access to components inside the inlet cowl. 2 inlets at the top let cool external air flow into the engine compartment for cooling, and a pressure relief door mechanically opens to release air pressure inside the inlet cowl. The outer barrel also has provisions for securing an inlet cover to protect the engine against flying object debris, FOD. The fan cowl door assemblies are engine-to-engine interchangeable units enclosing the engine fan case between the inlet cowl and the thrust reverser cowl. Each assembly is supported by 3 hinges at the pylon and latched to the other fan cowl along the bottom split line with 3 tension hook latches. The left fan cowl door contains a starter override access hole that allows access to the starter override valve. The right fan cowl door contains a pressure relief oil fill access door that provides an outlet for excessive pressure within the fan cowl area of the engine and is also used as an oil fill access door for the oil tank. A FADEC static port mates to the FADEC flange when the fan cowl is closed, and an exhaust grill is designed to prevent flammable fluids and vapors from collecting inside the fan cowl area. The fan cowl may be opened to a maximum of 60 degrees and is held open by a rod which is stowed on the fan cowl. The aft core cowls are located downstream of the thrust reversers and constitute the aft end of the engine core cowl, also serving as a pressure wall and a fire barrier between the engine core compartment and the fan duct. Both aft core cowls can be opened to provide engine maintenance, are linked to the pylon by 3 hinges, and held together at 6 o'clock position by 3 latches. The doors are held open by support rods, which are mounted on each aft core cowl door. Note, the thrust reverser cowl must be opened before the aft core cowls can be opened. The left aft core cowl has an operability bleed valve to allow engine bleed valve airflow to be discharged into the fan duct. and has a pressure relief door to minimize the amount of overpressure that can exist if an engine high-pressure duct fails. The right aft core cowl contains an engine oil service door used to access the oil filler port and an IDG oil side glass door to access the IDG side glass. The engine mounting system supports the engine by transmitting loads from the engine case to the pylon structure. It also maintains engine location and alignment under gravity. Engine thrust, acceleration, and gyroscopic pitch and yaw loads encountered during any flight condition. The system isolates airframe deflections from the engine during any flight condition, accommodates thermal expansion of the engine, and permits simple engine installation and removal. Each engine is connected to the pylon by a forward and an aft mount. The front mount attaches the fan OGV frame to the pylon and absorbs vertical, side, and torque loads. The aft mount attaches the engine mount ring and front frame to the pylon and absorbs vertical, side, and thrust loads. The engine nacelle fire seals, made of fireproof materials, separate the cavities located between the engine and nacelle into sealed compartments to prevent the propagation of fire. The fire zone boundaries include the fan compartment and the core compartment. Each compartment has independent detection and fire extinguishing capability. The inner fixed structure, IFS, of the thrust reverser core cowl forms the forward part of the engine core compartment fire zone and is covered on its inner side by fire blankets. The aft core cowl, ACC, forms the aft end of the fire zone and is made of an aluminum skin which contains a fireproof titanium sheet that is installed on the upper quadrant. A seal separates the forward IFS and the aft core cowl to form a zone closed off from the rest of the engine. The engine and nacelle drain system consists of lines and openings that direct any waste fluids from the engine and nacelle overboard. Two drain masts are used to discharge the drain fluids from the engine zones. The forward mast contains the accessory gearbox components and pad drains, as well as the oil scupper and pylon drains. The aft mast contains the fuel drains from the core-mounted components and the core pylon drain. The engine and nacelle drain system collects waste fluids that may accumulate during any abnormal operation. Oil is captured from the oil drain tube, the A-sump drain, and the air oil separator. Fuel is collected from the VGV actuators, the fuel pump pad on the accessory gearbox, the operability bleed valve, and the pylon. Hydraulic fluid is collected from the hydraulic pump on the accessory gearbox and from the pylon. The force of gravity drains the fluids to a drain mast at the lowest point in the system, where they are discharged overboard. The drain mast is located behind the engine air intake, so that waste fluids will not be sucked into the intake. Fluids in the nacelle cavities drain directly from the cavity to the outside of the nacelle, through drain holes which are provided in the nacelle cowls. The CF34-10E engine is a high-bypass turbofan engine, which is a fully integrated engine with nacelle and thrust reverser. The core engine consists of the following modules: the fan module, the core module, the low-pressure turbine module, and the accessory gearbox module. The engine has a two-frame and two-sump structural design. The fan module contains a 53-inch, 1,173 millimeter diameter single-stage fan and a three-stage low-pressure axial booster. The core module contains a 9-stage axial core compressor with bleed ports for customer bleed air connection at stages 5 and 9, a single annular combustion chamber liner, a single-stage axial core air-cooled high-pressure turbine. The low-pressure turbine module contains a non-cooled 4-stage low-pressure turbine that drives the fan and axial booster. The accessory gearbox, mounted on the fan case, provides mounting pads for IDG and the hydraulic pump. The engine low and high pressure rotors are supported by 6 main engine bearings. The low pressure rotor is supported by the number 1 thrust ball bearing, the number 2 and number 5 roller bearing. The high pressure rotor is supported by the number 3 thrust ball bearing and the number 4 roller bearing. The compressor rotor front shaft and the transfer gearbox are supported by roller bearing number 3. A dual-channel, full-authority digital electronic control, FADEC, provides flexible engine operation, reduced pilot workload, and the highest level of reliability, safety, and maintainability. The fan rotor and booster assembly provides the main thrust of the engine and also delivers air into the compressor section through the fan frame assembly. The low-pressure turbine rotor, via the fan drive shaft, provides driving power to the assembly. The fan rotor and booster assembly main components are the fan rotor spinner, the fan rotor spinner support, the fan rotor blade retainers, the fan blade spacers, the Stage 1 fan rotor disc, the fan rotor Stage 1 blades, the Stage 1 fan rotor blade shims, and the booster assembly. The aluminum fan rotor spinner is part of the fan rotor Stage 1 blade retention system. For fan balancing, the mid-flange has tapped holes to install the trim balance screws. The design of the nose cone prevents ice formation. The fan rotor spinner is bolted to the fan rotor spinner support that again is bolted to the Stage 1 fan rotor disc. "24 fan rotor blade retainers are installed between the disc posts of the Stage 1 fan rotor disc and bolted to the fan blade spacers to limit the axial movement of the fan blade spacers. The retainers and the spacers are both part of the fan rotor Stage 1 blade retention system. The fan blade spacers are installed between the dovetail slots of the Stage 1 fan rotor disc and the fan rotor blade shims to limit the radial movement of the fan rotor blade retainers. The Stage 1 fan rotor disc is a titanium alloy forging. Its inner rear flange provides attachment for the fan shaft, and its outer rear flange is bolted to the booster spool. The outer front flange supplies attachment for the fan rotor spinner and the fan rotor blade retainers. The inner front flange supplies attachment for the fan rotor spinner support. The outer rim of the Stage 1 fan rotor disc has 24 dovetail slots designed for fan rotor Stage 1 blade retention. 24 titanium alloy wide chord fan rotor Stage 1 blades are installed in the Stage 1 fan rotor disc. Each of the fan blades has a dovetailed base that engages in the dovetail slots of the Stage 1 fan rotor disc. Blade shims are installed in the dovetail slots blade to limit the radial movement of each fan blade. The booster assembly consists of the booster spool, the Stage 2 through 4 fan rotor blades, which serve primarily to supercharge the compressor rotor assembly, and the Stage 1 IGV through Stage 4 vane assemblies. The booster assembly is mounted on the rear of the Stage 1 fan rotor disc and acts as a stop for the fan rotor Stage 1 blades. The fan frame assembly is the main forward support for the installation of the engine to the aircraft. It supports the fan and booster assembly and compressor rotor assembly and supplies ducting for primary and secondary airflows. The fan frame assembly consists of the fan frame, the aft fan case, the OGV fan stator vane assemblies, the fan outlet guide vane fairing, the splitter, and the fan stator containment case. The aft fan case provides an inlet airflow path to the core engine and houses the accessory drive PTO bevel gears and driveshaft assembly, the variable bypass valve system, and provides attachment points for the OGV fan stator vane assemblies. The fan frame is a basic 12-strut hub structure that provides supports for the PTO and the number 1 and number 3 bearings. The hollow struts have passages for equipment like the fan speed sensor and oil lines. The mid-box front structure, located between the primary and secondary airflows, houses the 12 VBV doors and 2 VBV actuators at the 1:30 and 7:30 o'clock positions. The OGV fan stator vane assemblies are individual vanes made of carbon fiber epoxy. The vane inner platforms are axially retained by the fan outlet guide vane fairing, while the vane outer platforms are attached with bolts to the aft fan case. The fan outlet guide vane fairing, mounted between the fan frame and the splitter, contains grommets that support the inner platforms of the OGV fan stator vane assemblies. The splitter is a fairing that divides the airflow into the booster assembly and fan bypass duct. The fan stator containment case provides fan rotor stage 1 blade containment in the event of a fan blade fracture. It also provides attachment points for the inlet cowl and houses the abradable liner for the fan rotor stage 1 blade tips. The compressor section is located between the fan frame assembly and the combustion section and includes the compressor stator assembly and the compressor rotor assembly. The compressor stator assembly is divided into a forward and rear compressor stator assembly and provides structural support for the engine between the front frame assembly and the combustion chamber frame. The compressor stator case consists of 2 halves joined at a horizontal split line that permits on-wing removal of the top case half. The compressor stator case includes 2 integral air manifolds and stage 5 and stage 9 ports for bleed air connections. Actuating arms and rings, controlled by the actuating system linkage assembly, control the position of the variable vanes of the intermediate guide vanes and stage 1 through stage 3. Stage 4 through stage 8 vane segments are installed into the ends of the compressor stator case and split on a horizontal plane to match the compressor case split line. The compressor rotor assembly, together with the compressor stator assembly, compresses the air and discharges this air into the combustion chamber. The compressor rotor is a 9-stage axial flow design with a pressure ratio of 11.4 to 1. Components are held together at the stage 3 disc joint and at the compressor discharge pressure seal joint, which creates a rigid drum. The compressor rotor assembly consists of the compressor rotor forward shaft, the compressor rotor stages 1 and 2 spool, the compressor rotor stage 3 disc, the compressor rotor stages 4 through 9 spool, the compressor rotor stages 1 through 3 blades, the compressor rotor stages 4 through 9 blades, and the compressor rotor rear rotating air seal. The compressor rotor forward shaft, bolted to the stage 3 disc, provides forward support for the compressor rotor assembly and contains splines that engage the compressor rotor assembly with the horizontal bevel gear of the power takeoff assembly. The combustion assembly is installed between the compressor section and the low-pressure turbine module assembly and provides a flow path between the compressor section and the low-pressure section. The combustion assembly consists of the combustion case, the combustion chamber assembly, the high-pressure turbine stator interstationary seal, and the turbine nozzle assembly. The combustion case contains bore scope inspection ports to access the combustion chamber, the high-pressure turbine rotor blades, and the Stage 1 low-pressure turbine blades. The annular combustion chamber assembly provides a housing for the ignition of the fuel-air mixture. Air that exits the compressor is diffused into the combustion case. The inner and outer liner, supported by the combustion chamber cowl, capture the compressor discharge air from metering the airflow to the dome. Most of the dome airflow passes through the primary swirlers into the reaction zone, where it serves as primary combustion air. The remainder of the dome airflow is used for dome cooling. The primary swirlers are fuel-air mixing devices which use high-energy air to atomize and aerate the fuel. The atomized mixture is introduced into the combustor reaction zone where it is ignited by the high-voltage igniters. Air that passes into the inner and outer passages of the combustion chamber shells serves as primary air cooling to reduce turbine inlet temperature cooling of the combustor shells and other engine parts. The turbine nozzle assembly is a single-stage air-cooled assembly that is mounted to the aft flange of the combustion chamber liner. The turbine nozzle assembly contains 19 high-pressure turbine stator nozzle segments that direct the gas flow from the combustion chamber assembly onto the high-pressure turbine rotor blades in the most optimal angle to permit the greatest performance during all conditions of operation. The high-pressure turbine Stage 1 nozzle assembly directs the force of hot, high-velocity, high-pressure gas into the Stage 1 high-pressure turbine rotor blades. The high-pressure turbine Stage 1 nozzle assembly consists of the inner high-pressure turbine nozzle support and the 24 Stage 1 high-pressure turbine nozzle segments. The nozzle segments, each with 2 vanes, are constructed of nickel alloy and are coated for environmental protection. The vanes are cooled by the compressor discharge air, which enters the vane segments at the top and exits the vanes through holes at the leading and trailing edges. The high-pressure turbine HPT module consists of the HPT rotor assembly and the HPT stator assembly. The high-pressure turbine rotor extracts energy from the combustion gases that exit the combustion liner and drives the compressor rotor assembly. The HPT rotor assembly consists of the HPT rotor disc, the HPT front rotating air seal, the HPT rotor front shaft, the HPT rotor blades, the HPT rotor rear blade retainer, the HPT rear rotating seal, and the HPT rear shaft. The HPT rotor disc provides an attachment point on the forward flange for the HPT front rotating air seal and the HPT rotor front shaft that connects the HPT rotor disc to the compressor. The HPT rotor blades have dovetail shanks that fit in slots of the HPT rotor disc and are axial locked in place by the HPT rotor rear blade retainer. The blade airfoil and platform are top-coated with a white ceramic thermal barrier coating to lower the metal temperature and improve part life. Blade cooling is performed by compressor discharge air that enters the blade root and is forced out through holes in the blade leading edge, trailing edge, and the blade tip. The HPT rear shaft, which is bolted to the HPT rotor disc, provides the aft support for the HPT rotor assembly. Seal teeth of the HPT rear shaft and the honeycomb of the inner forward air rotating seal of the LP shaft assembly form a seal for the number 4 roller bearing sump. The low-pressure turbine, LPT, rotor and stator assembly converts gas energy to rotational force required to drive the fan rotor and booster. The LPT rotor consists of a 4-stage, tip-shrouded blade disc assembly and the stage 1 to 4 low-pressure turbine nozzles. The stage 1 low-pressure turbine nozzle, which is mounted in the combustion case, is impingement cooled by high-pressure compressor 4th-stage bleed air. All other low-pressure turbine nozzle airfoils, stages 2 through 4, which are mounted in the low-pressure turbine case, are not air-cooled. To prevent air leakage between the 4 low-pressure turbine stages, integral inner seals on the low-pressure turbine nozzles run against interstage seals that are mounted on the low-pressure turbine rotor. The stages 1 through 4 shroud segments have open-face honeycomb wear surfaces to minimize air leakage at the LPT blade tips. The LPT rotor consists of a 4-stage tip-shrouded blade disc assembly. The 4 discs and the interstage seals are fastened together with close-fitting bolts. The low-pressure turbine assembly is bolted to low-pressure turbine shaft via the stage 3 disc and interfaces with the fan drive shaft with splines. The stage 1 to 4 low-pressure turbine blades are held in the discs by retainers, while the shrouded blade tips have interlocks that keep them rigid. The LPT case contains the LPT nozzle segments and the LPT shroud segments. The non-air-cooled stage 3 through 6 nozzle vane segments have integral inner seals against the interstage seal. The stage 3 through 6 shroud segments have open-face honeycomb wear surfaces to minimize air leakage at the LPT blade tips. The turbine exhaust frame assembly is the third of 3 major structural frames in the engine. It is also the main structural support for the low-pressure turbine rotor and stator assembly. The turbine exhaust frame assembly supports the C-sump, which houses the number 5 bearing outer races. The inner and outer cases are connected by 6 struts located at the 2, 4, 6, 8, 10, and 12 o'clock positions. The 6 struts support the inner hub, which supports the C-sump and the number 5 bearing. Service lines into and out of the C-sump are routed through 3 of the 6 struts. The engine accessory gearbox, AGB module, is a mechanical system that translates engine power to drive the engine accessories. The drive systems consist of the accessory gearbox, AGB module, the transfer gearbox, TGB, the radial drive shaft, and the inlet gearbox, IGB. Drive power from the engine to the accessory gearbox assembly is provided by a bevel gear installed on the high-pressure compressor rotor assembly, which interfaces with the inlet gearbox bevel pinion gear. The inlet gearbox bevel pinion gear is splined to the radial drive shaft, which passes through the 10 o'clock strut in the fan frame assembly to drive the transfer gearbox. The transfer gearbox assembly, installed on the fan frame at the 9 o'clock position, provides power transmission between the inlet gearbox assembly and the accessory gearbox module, and consists of the outer radial drive shaft, the transfer gearbox, and the horizontal shaft. The outer radial drive shaft is installed inside the number 10 strut of the fan frame and is on one end internally splined to the inner radial drive shaft and on the opposite side externally splined to connect with the transfer gearbox axis of pinion bevel gear. The horizontal shaft supplies power transmission between the transfer gearbox and the accessory gearbox assembly and is splined at both ends. One end of the horizontal shaft connects with the accessory gearbox gear shaft, and the other end of the horizontal shaft connects with the splines of the axis B wheel bevel gear. The accessory gearbox, AGB, is rigidly supported by the fan frame at 3 locations and is a cast 2-piece housing, with drive pads on the forward and aft faces of the gearbox to allow mounting of the accessories. The aft face of the accessory gearbox provides mounting pads for the lube and scavenge oil pump, the oil filter manifold, the engine-driven fuel pump, and the input connection for the horizontal drive shaft. The front face of the accessory gearbox provides mounting pads for the engine-driven hydraulic pump, the PMA, the air turbine starter, and the IDG. A drain plug is located at the 7 o'clock position to allow drainage of the accessory gearbox cavity for shipping or troubleshooting purposes. The engine fuel system has 2 subsystems, a fuel control system and a fuel distribution system, which provides the engine with scheduled fuel for combustion. The engine fuel control system is composed of a 2-channel full authority digital electronic control, FADEC, a fuel metering unit, FMU, a permanent magnet alternator, PMA, engine sensors, variable stator vane and bleed valve actuators, a transient bleed valve, TBV, and the high-pressure turbine clearance control, HPTCC valve. The components of the fuel distribution system include the fuel pump, fuel filter, 2 fuel manifolds, and 20 fuel injectors. The fuel distribution system starts when the fuel from the aircraft fuel tank enters the engine fuel pump inlet, where the fuel pressure is increased by a centrifugal boost pump located in the engine fuel pump. Fuel discharged from the boost pump splits inside the pump housing and is either returned via the positive displacement motive gear stage to the aircraft as motive flow or routed toward the main gear pump inlet. The flow that is not directed to the aircraft as motive flow leaves the boost pump and joins up with the return or bypass flow coming from the FMU. This combined flow then passes through the main fuel oil heat exchanger to cool the engine lubricating oil. The fuel oil heat exchanger also heats the fuel to provide icing protection in the event of trapped water in the fuel during cold day operation. After passing through this heat exchanger, the fuel returns to the inlet or low pressure side of the fuel pump main gear stage element. The pump main gear stage total flow passes through the main fuel barrier filter and servo wash filter. The servo flow coming through the wash filter is directed separately to the FMU, where it is used to supply the electro-hydraulic servo valves, EHSV. The EHSVs operate the fuel metering valve, FMV actuator, the variable stator vane, VSV actuators, the variable bypass valve, VBV actuators, the high-pressure turbine clearance control, HPTCC valve, and the transient bleed valve, TBV. The main flow exiting the fuel filter is directed to the inlet of the FMU. Fuel entering the FMU passes through the inlet pressurizing valve, IPV, and then enters the bypass valve. At the bypass valve, the fuel is either returned to the pump or is directed to the metering valve. The metering valve is positioned by the FADEC to provide the proper burn flow to the combustion chamber fuel injection nozzles. Metered fuel flow exits the FMU through the shutoff valve to the 2 fuel manifolds, where it is distributed to the 20 fuel nozzles. The fuel control system is managed by a 2-channel full-authority digital electronic control, FADEC. The FADEC controls the engine fuel requirements in response to thrust command inputs from the aircraft. The FADEC software provides thrust management based on aircraft and air data inputs. These inputs are used to calculate appropriate reference N1 for any given throttle position. Some of the N1 references are modified by discrete inputs like Automatic Takeoff Thrust Control System, ATTCS, Thrust Reverser Position, Weight on Wheels, and Bleed discrete inputs. In addition to setting the correct N1 for a given TLA position, the FADEC schedules limit fuel to protect the engine speeds, temperature, and compressor discharge pressure, CDP, limits. The fuel pump, mounted on the aft face of the accessory gearbox, provides sufficient fuel flow and pressure to meet engine burn flow requirements, as well as fuel for the fuel-operated actuators and valves, and motive flow for the fuel tank ejector pumps. The fuel pump consists of a centrifugal boost element and 2 fixed displacement high-pressure gear elements. The fuel pump has a spline drive shaft that engages a wet spline within the AGB pad, and a V-band coupling secures the fuel pump to the accessory gearbox. Filtration of the fuel system is provided by a main fuel filter, which is mounted at the 3 o'clock position of the fan case. The filter contains a differential pressure switch that provides indication in the event of an impending bypass. In the event of a complete filter blockage, a bypass valve opens to ensure fuel supply to the FMU. To minimize fuel spillage during fuel filter replacement, the filter bowl contains a drain plug to drain the filter bowl before removing the filter element. The fuel metering unit, FMU, is mounted on brackets that are attached to the fan case at the 5 o'clock position. The main purpose of the FMU is to provide accurate metered fuel flow to the engine for combustion. The FMU also provides fuel flow for variable stator vane and variable bypass valve actuation, operates the high-pressure turbine clearance control valve and the transient bleed valve, and provides fuel shutoff for normal engine shutdown and for overspeed protection. The fuel from the main fuel barrier filter and servo wash filter enters the FMU where it passes through the inlet pressurizing valve, IPV. The fuel then enters the bypass valve and is either returned to the pump or passes through the valve to the metering valve. The metering valve is positioned by the FADEC to provide the proper burn flow to the fuel nozzles. Metered fuel flow exits the FMU and passes through the fuel manifold, where it is distributed to the 20 fuel nozzles. The fuel manifold is located around the circumference of the combustion chamber frame, just aft of the forward flange. Fuel coming from the FMU enters the fuel manifold and is distributed to the 20 fuel nozzles. The fuel injectors receive the metered fuel from the FMU and atomize it into the domed combustor. Based upon the fuel pressure delivered, a distributor valve located in the fuel injector ports fuel to the primary and secondary fuel flow circuits. The primary circuit is used during start and low power, while the secondary circuit provides additional flow at high power. Each fuel injector has a check valve that closes at engine shutdown to prevent the manifolds from draining into the combustor. The variable bypass valve system controls the booster operating limits, provides optimum booster performance at steady-state conditions, and prevents stall. The system consists of 2 VBV actuators which operate via adjustable links, bell cranks and actuating rings, 10 VBV doors that open to bleed excess booster discharge airflow or close to allow zero bleed. The VBV system is controlled by the FADEC and operates from idle, doors open, to takeoff power, doors closed. During reverse thrust, the FADEC will partially open the VBV doors to increase booster stability and to prevent core engine foreign object damage. During engine shutdown, the VBV doors are driven open. The FADEC determines the required VBV position based on engine sensor inputs and sends an electrical signal to the FMU, which supplies servo fuel to both VBV actuators. Movement of the actuators will open or close the 10 VBV doors. Each of the 2 actuators contains a single LVDT. One actuator provides bleed valve position feedback to the in-control FADEC channel, while the other actuator provides position feedback to the standby channel. The variable stator vane, VSV, actuation system varies the angle of attack of the variable compressor stator vanes to maintain a smooth, turbulence-free airflow through the compressor rotor at all engine operating speeds, temperatures, and altitudes by means of 2 VSV actuators that are mounted on 2 sides of the forward compressor stator case. The FADEC continuously determines the needed VSV position based on engine sensor inputs and sends, when required, an electrical signal to the FMU, which sends servo fuel to both VSV actuators. Movement of the actuators will adjust the compressor stator vanes to the required position via torsion tubes, links, and actuating rings. Each of the 2 actuators contains a single LVDT. One actuator provides stator vane position feedback to the in-control FADEC channel, while the other actuator provides position feedback to the standby channel. The transient bleed valve, TBV, system bleeds air from the compressor rotor to provide compressor stall margin. Using aircraft and sensor inputs, the FADEC uses fuel metering valve servo fuel to open the transient bleed valve during engine starts and during engine transients to protect the engine stall margin. When the transient bleed valve is commanded open, compressor discharge air is exhausted overboard into the exhaust nozzle. Dual LVDTs attached to the valve provide position feedback to each FADEC channel. During normal engine operation, The fuel metering valve is set to the desired flow position, and the bypass valve bypasses the excess pump flow needed to maintain the appropriate differential pressure across the fuel metering valve. At engine speeds below 20%, the pressurizing shutoff valve sets a low pump differential pressure setting of plus or minus 150 psid. As engine speed increases, system pressure regulation is transferred to the IPV, which has a much higher setting, plus or minus 350 psid, for actuation of the engine variable geometry system. The IPV maintains this pressure level until the FMU's back pressure overcomes the IPV setting. The shutoff overspeed valve is positioned so that boost pump pressure is ported behind the pressurizing valve, and so that the bypass valve's compensating land is deadheaded. The shutoff overspeed valve is positioned by the overspeed solenoid, which supplies high pressure to the valve in order to obtain the necessary force margin. A repeatable flow schedule is accomplished by maintaining a constant differential pressure across the fuel valve port. Therefore, metered flow is a function of valve area, and therefore valve position. The flow versus position schedule is digitally mapped into the control software of the FADEC. Fuel sent to the combustor can therefore be scheduled by simply positioning the fuel metering valve, FMV. Additionally, the FMU sets a minimum differential pressure across the high-pressure pump at engine starting and low-metered fuel conditions. This function is required for hydraulic actuation of the engine variable geometry, as well as for positioning control within the FMU. Metered flow passes through the pressurizing shutoff valve and exits the FMU to be burned in the engine combustor. In addition to setting a low pressure for start and relights, the pressurizing shutoff valve provides a zero-leak shutoff following operation of either the overspeed system or after normal shutdown. During normal operation, the VSV, VBV, HPTACC, and TBV actuators are positioned by the FADEC by a current command to the dedicated electrohydraulic servo valve, EHSV, within the FMU. The LVDT feedback from the actuators is used to close the position loop through the FADEC. The VSV actuator position demand is computed in the FADEC as a function of corrected in2. The position demand is modified during transient operation and during combustion chamber relights to overclose the stators and maintain compressor operability margins. The VBV actuator is positioned by the FADEC as a function of corrected in1. The position demand is modified during transient operation to maintain booster operability margins. During steady-state engine operation, the TBV will be commanded closed. During transient operation, combustion chamber relights, and engine starting, the TBV is scheduled open in order to bleed the compressor and maintain compressor operability margins. The HPTCC valve position demand is computed in the FADEC software to optimize the turbine clearance as a function of the engine operating conditions. The core speed rotor provides overspeed protection. The fan rotor will not overspeed unless the core rotor first overspeeds. When an overspeed condition is detected, for example, the core rotor is greater than 102% RPM, the fuel shutoff solenoid in the FMU closes, causing an engine flameout. Dedicated electronic speed switches in the FADEC provide overspeed protection. Each FADEC channel has 2 speed switches that monitor the core rotor speed. One speed switch uses the speed signal from the alternator, and the other speed switch uses the speed signal from the in2 speed sensor. Both switches must close to flame out the engine. The overspeed system in both channels is always active regardless of which channel is in control. The engine fuel indicating system is monitored by engine-mounted sensors which give their information to the ICUS. The indicating system consists of a fuel filter bypass switch, a fuel low-pressure switch, and a fuel flow measuring device. The fuel filter impending bypass sensor, mounted in the fuel filter housing, senses the pressure drop between the inlet and the outlet of the fuel filter. Should the pressure drop across the fuel filter caused by filter contamination exceed the specified limit, a signal is sent via the MAU to the ICUS to indicate that the filter is at impending bypass. The fuel low-pressure switch is mounted in the fuel feed line near the fuel pump inlet. The switch senses the fuel pressure going into the main fuel pump supply line. When the fuel pressure drops below a predefined value, a signal is sent via the MAU to the ICUS. Fuel flow indication is not measured by a common fuel flow transmitter. Rather, the fuel flow is measured by the FMU metering valve. The metering valve position is converted to fuel flow in a lookup table in the FADEC and transmits this signal via the MAU to the ICUS fuel flow indicator as pounds or kilograms per hour. Fuel flow indication is not measured by a common fuel flow transmitter. Rather, the fuel flow is measured by the FMU metering valve. The metering valve position is converted to fuel flow in a lookup table in the FADEC and transmits this signal via the MAU to the ICUS fuel flow indicator as pounds or kilograms per hour. The engine control system provides steady-state and transient regulation of thrust while protecting the engine compressor aerodynamic and aeromechanical stability limits, combustion blowout limits, and the fan and compressor rotor mechanical limits. The system also provides independent protection of compressor rotor overspeed, but does not provide explicit protection against a turbine temperature over-temperature with the exception of ground starts. Engine fuel system operation begins with information supplied by the FADEC and provides steady-state and transient regulation of thrust while protecting engine limits. One FADEC channel operates as the in-control FADEC channel, providing electronic control outputs. The other FADEC channel operates as the standby FADEC, processing all inputs but with all electronic control outputs disabled during normal engine operation. During operation with two capable FADEC channels, in-control software logic will cause the FADEC channels to alternate control on each successive engine start. Main FADEC power is supplied by the PMA during engine operation, with a 28-volt DC airframe input for starting and backup. The in-control FADEC channel and the FMU automatically initiate fuel flow and ignition in response to engine core speed information from the starter. In-control selection is made at 6.7% N2, and the FMU is pressurized in order to control the metering valve at approximately 6.7% N2. For ground starts, the ignition is commanded on at approximately 9.5% N2, and fuel is introduced at approximately 20% N2. After a light-off occurs, the in-control FADEC channel commands the starter cutout at approximately 50% N2 and controls the FMU fuel metering valve to accelerate the engine to the thrust setting calculated from the FADEC inputs. Thrust control of the engine is provided by the FADEC with thrust management based on aircraft and air data inputs. The main thrust setting inputs are the thrust lever angle, TLA, and the air data from the engine and airframe sensors. These inputs are used to calculate appropriate reference N1 for any given throttle position. During normal engine operation, the FADEC will control to a physical N2 or a P3 reference at idle throttle settings, and to a physical N1 reference at any power above idle up to maximum power. The FADEC uses the following propulsion system signals to control the fuel to the engine. N1 fan rotor speed, provided from the N1 speed sensor that produces a frequency output derived from a 25-tooth wheel on the fan shaft, proportional to the fan speed. N2 core rotor speed, provided by the N2 sensor mounted on the accessory gearbox and from the engine-mounted alternator, PMA. T2 total ambient temperature, taken from the dual T2 temperature sensor mounted in the engine air intake and from the aircraft total air temperature sensors. T25 compressor inlet temperature, provided by a sensor mounted in the flow stream in front of the compressor. T3 compressor discharge pressure, provided by a sensor mounted in the flow stream in the rear of the compressor. T49.5 enter turbine temperature, taken from 3 electrically identical ITT probe assemblies, each consisting of 3 dual thermocouples, which are arranged circumferentially on the turbine case. Position of the fuel metering valve, FMV, inside the FMU, which is measured by a dual-wound linear variable differential transformer, LVDT. The variable stator vane actuator position also measured with a dual-wound LVDT. The variable bypass valve actuator position measured with a single-wound LVDT in each actuator. The high-pressure turbine clearance control HPTCC valve measured by a dual-wound LVDT. The transient bleed valve actuator position measured by a dual-wound LVDT. Thrust reverser position taken from thrust reverser, TRAS, actuators number 3 and 4 have an LVDT and a locked switch that are read by the FADEC. Engine compressor discharge pressure, PS3, taken from the combustor case and sent forward through a pressure line to the FADEC P3 pressure transducers. Alternator power from the engine supplied PMA and engine inlet static pressure, P0, which is taken by a transducer mounted inside the FADEC, and from the aircraft pitot tubes mounted on the forward section of the fuselage. The FADEC also uses the following aircraft system signals to control the engine. The aircraft Mach number, the flap position, wheel speed, radio altimeter, TLA selection, weight on wheels, landing gear position, bleed system selection, and information from the engine identification and configuration plug. The engine configuration plug, ECP, mounted to the FMU bracket provides data that is read by the FADEC at the time of power-up on the ground. The ECP provides information on the engine serial number, engine thrust rating, hardware configuration, and N1 modification, N1 trim. The FADEC will validate the engine configuration by comparing the engine configuration from the ECP to the FADEC software. Similarly, the FADEC will validate the aircraft application by comparing the aircraft application from the APPID to the FADEC software. If the FADEC cannot accommodate the aircraft application, the FADEC will transmit the appropriate ICAS messages to the cockpit. The aircraft MAU will also compare the engine ratings from both engines as a validity check.